Welcome to the deep dive. Today, we're plunging into the world of some really quite tricky problems, the ones we call NP problems.
Right.
You probably know the kind I mean. Finding a solution can feel impossible, like finding a specific atom somewhere out in the universe.
Yeah.
But if someone actually hands you a potential solution...
Checking it is surprisingly fast, relatively speaking, anyway.
Yes, exactly. Like Sudoku, right?
Yeah.
Sometimes feels super hard to solve, but checking a finished grid, easy.
That's the basic idea, yeah. Verifiable quickly, but potentially incredibly hard to solve from scratch.
And we're tackling a really interesting, maybe even counterintuitive question about these things today. Do they actually have predictable patterns, like especially when it comes to when they become solvable or just plain unsolvable?
It does sound a bit strange, doesn't it, putting predictable next to NP complete. But yeah, that's exactly what some research is digging into, how the actual structure of these problems, you know, the number and the type of constraints they have can lead to these really surprising thresholds, sudden cliffs almost.
Okay, and that leads us straight to the source material for this deep dive. It's a study called Transitions of Critical Structural Regions for NP Problems. And it looks right at this phenomenon. It even proposes a specific mathematical tool, something called the Changbal Function, to try and describe these critical points.
Yeah, it's an attempt to find maybe a more unifying way to look at these sharp changes and how hard a problem is, moving beyond just looking at one problem type like SAT and trying to see if there's something fundamental about the structure itself.
Right. So our mission today is clear. Let's unpack this research. We want to understand what these structural transitions really are, get our heads around this Changbal function idea, and figure out the most important takeaways about finding predictability in these seemingly chaotic problems.
Okay, sounds good. Where should we start? Maybe a quick refresher on NP itself.
Good idea.
So NT problems, right? The key is verification takes polynomial time, which basically means fast relative to how big the input is. Finding the solution, though,
that's the killer.
that can take exponential time. It gets computationally, well, let's just say infeasible very, very quickly as the problem size grows. Especially for the NP-complete ones, those are the hardest nuts to crack in the NP class.
And this research, it really hammers home that the difficulty isn't always a smooth climb. It's not like walking up a gentle hill.
No, not at all. The paper talks about abrupt transitions in solvability.
Like you said, hitting a cliff edge.
Exactly. You're cruising along, things seem okay, maybe getting a bit harder, and then bam, suddenly it's practically impossible to find a solution.
And this isn't a totally new observation, right? It builds on earlier work.
Oh, definitely. There's a lot of history here, especially looking at computational phase transitions. The big one is the satisfiability problem, SAT.
Ah, SAT, yeah.
The source we're looking at even calls SAT a canonical domain. I think they even say it's the Bible for studying this kind of thing.
Wow.
Because researchers noticed years ago that with SAT, as you added more constraints, more clauses relative to the variables, you'd hit this sweet spot, or maybe a sour spot, where the problem suddenly became drastically harder to solve. A phase transition.
So taking that foundational idea from SAT, this paper introduces the Changbal function. What's the core idea there?
Okay, so they propose the Changbal function as a way to model SOL. That's the probability of finding a solution for a given instance of an NP problem.
SOL.
And the crucial part is that they model this SOL as a function of D, which they call constraint density.
Constraint density. So, like, how many rules or connections there are packed into the problem. More constraints, higher density.
Precisely. It's a measure of how restricted, how hemmed in the problem is. And the picture to have in your head, the key shape of this Changbal function is sigmoid.
An S-curve.
Right.
Like you see in biology sometimes, or learning curves.
Exactly like that S shape. And what that shape captures perfectly is the nonlinear shift. So the probability of finding a solution, SOL, stays high for a while even as you add constraints. Then, over a really quite narrow range of this constraint density, it just plummets incredibly fast. And then it levels off again, but down near zero probability.
So it's not a gentle slope down, it's a really rapid drop-off.
A very rapid drop. That's the essence of the transition they're modeling.
And I assume this function has, like, mathematical knobs you can turn, parameters?
Yeah, it does. The formal definition they give is SOL. SOL1 divided by 1 plus e to the power of minus alpha times d minus dc.
Okay, let's break that down. D is the constraint density we talked about.
Right. Then DC is the critical threshold density. Think of that as the exact center point of that steep drop. It's where the cliff is sharpest.
Got it. The midpoint of the plunge. And alpha.
Alpha is the steepness parameter. It tells you how sharp that drop is. A bigger alpha means a more vertical cliff face, a more abrupt transition.
Okay, so DC positions the cliff, alpha defines its steepness. Makes sense.
Yeah. And they're quite clear that, while they've given it this name, the Changbal function, the underlying sigmoid shape itself is heavily inspired by those kinds of thresholds people had already seen empirically in problems like SAT.
Okay, so you've got this theoretical function. How do you actually test it? They needed a concrete problem to work with, right?
They did, and they chose something called the two-coloring problem on K-uniform hypergraphs.
K-uniform hypergraphs. Sounds complex.
It might sound a bit abstract, but it's actually a really good choice. K-uniform hypergraphs are used to model all sorts of complex interactions you find in the real world: social networks, biological systems, data relationships.
Okay, so what is one? How is it different from a regular graph?
In a regular graph, an edge just connects two vertices. Simple. In a hypergraph, you have hyperedges. And a K-uniform hyperedge connects exactly K vertices all at once.
So instead of pairs, a hyperedge links a group of K things together. Like a team.
That's a great analogy. A team of exactly K players. Now, for the two-coloring problem on this structure.
Right, what's the goal?
You need to assign one of two colors, let's just say red or blue, to every single vertex, every player. And the rule, the constraint, is that every single hyperedge, every team, must contain at least one player of each color.
Okay, so you can't have a team where everyone's wearing red or everyone's wearing blue. Every team needs diversity.
Precisely. No monochromatic teams allowed.
And you mentioned this gets hard.
Yeah, it's known to be NP complete for A greater than or equal to 3. If K is 2, it's just standard graph two-coloring, which is easy. But as soon as your teams have 3 or more members, KO3, the problem jumps into that really hard NP complete category.
Which makes it a perfect test bed for looking at these sharp transitions in difficulty.
Exactly. It's got the complexity, and previous work hinted that it might show these abrupt changes in solvability depending on how many constraints, how many hyperedges you have.
Okay, so they've got their problem.
Yeah.
How do they actually run the experiments? What was the setup to try and map out this solvability cliff?
Well, they essentially generated a whole bunch of these hypergraphs and tried to solve the two-coloring problem for each one. They started by fixing the number of vertices in.
Okay, a set number of players.
Right. Then they experimented with different team sizes, K. The paper focuses specifically on K3, K4, and K5.
Got it. And then presumably they started adding the rules, the teams.
Exactly. They systematically varied the number of hyperedges, M, and that's what directly controls the constraint density, D, N, E, N. They increased N steps, going from 0.5 up to 5.0 in their experiments. So they were gradually making the problem more and more constrained, adding more and more teams that needed that red-blue mix.
And for each specific setup, like N100, Kegel3, and a certain number of edges, how did they figure out if it was solvable?
They used a random generation process. For a given N, K, and M, they'd treat M hyperedges by randomly picking K vertices for each hyperedge. Then they'd throw a solver at it. Basically an algorithm designed to find a valid two-coloring if one exists. The outcome was binary. Yes, a coloring was found solvable, or no, it wasn't unsolvable within the solver's limits.
Just yes or no.
Yeah.
But one try might just be lucky or unlucky, right?
Right. So to get a reliable picture, they used an empirical approach. For each combination of N, K, and M, they repeated this whole process, generate a random instance, try to solve it 100 times.
100 attempts for each data point.
Yes. And that gave them the empirical success rate. You know, what percentage of those 100 random instances turned out to be solvable for that specific configuration.
Okay, so now they have success rates for different constraint densities.
Exactly. And then they could plot that success rate against the constraint density.
Right.
That's where you hope to visually see the transition, the cliff.
Oh, they did they. What did figure 1 of the paper show?
Oh, it showed something pretty dramatic, especially for K3. For K3, when the constraint density was low, the success rate was consistently high, close to 1.0, almost always solvable. But then, as it got close to about 2.5, the success rate just plummeted. It dropped incredibly sharply, hitting almost 0 very quickly after that point. That was the cliff, clear as day.
Wow. So a really undeniable transition for K3, right around density 2.5. What about the others, K4 and K5?
Well, interestingly, for K4 and K5, at least within the range of densities they tested in this specific set of experiments, the success rate basically stayed pinned near 1.0. It remained very high across the whole range from D.5 to D5.0.
So no cliff observed for the larger hyperedges, the bigger teams, within those experimental boundaries.
Correct. Not in that particular setup. It doesn't mean a cliff doesn't exist for K4 or 5, maybe just at a higher density than they probe here, or perhaps with different parameters. But within these results, the action was all at K3.
And that sharp drop they saw for K3, that's what they're labeling the Changbal region.
Yes, formally they define the Changbal region as that range of constraint densities, where the slope of the solution probability function, the steepness of the S-curve, is greater than some threshold value. They call it a narrow emergence region.
Well, it's literally the steepest part of the curve.
Exactly. It pinpoints this structurally induced transition. And the fact that the success rate just flatlined near zero after that K3 threshold is really strong evidence. It suggests the transition is inherent to the problem structure at that critical density, not just an artifact of the specific solver they used or the size of the instance.
Okay, so the experiments seem to back up the idea of this sharp, structurally driven transition, at least for K3 hypergraph coloring. Let's zoom out a bit. What are the really big picture insights here, the main takeaways?
Right, let's distill it. What are the key things to remember from this?
Lay them on me.
Okay, first off, seeing this kind of phase transition in hypergraph coloring, which looks structurally quite different from SAT, but showing a similar pattern, it strongly suggests this isn't just a weird quirk of SAT. It's probably a much more general phenomenon across NP-complete problems.
So, insight one. The complexity cliff is real and widespread. Even these incredibly hard problems might have these hidden structural tipping points.
Exactly. And the way it behaved for K3, that sharp collapse, shows an extreme sensitivity to constraint density right around that critical point DC. And the uniformity K, the size of the hyperedges, seems to really matter. Higher K means the interactions between constraints get way more complex, much faster. Adding just a few more constraints, especially those involving more vertices, can suddenly push the whole system over the edge.
It really points to the structure itself, the rules of the game being the driver.
It strongly supports that, yeah. It's likely less about the algorithm struggling and more about the fundamental nature of the solution space collapsing or becoming disconnected.
Okay, what's the second big insight? This one feels, well, really interesting. Order from chaos. Predictable patterns coming out of problems we think of as fundamentally non-deterministic.
It is fascinating, isn't it? NP problems are kind of the definition of computational unpredictability in many ways. Yet this study, and others like it, show these remarkably predictable, very sharp transitions. The paper uses phrases like emergent solvability or unsolvability being a structural inevitability once you cross that critical density threshold.
A structural inevitability. Wow. So the constraints themselves, once they reach a certain density, effectively dictate the outcome. Like the fate of the problem solvability is sealed by its structure at that point.
That's the hypothesis emerging from this line of research. It really challenges the perhaps overly simplistic view that all NP-complete problems are just uniformly hard everywhere. It suggests structure can create these very defined regions of solvability, or in this case, sudden cliffs of unsolvability.
Okay, and insight three, connecting it back to the real world.
Right, relevance. We mentioned hypergraphs are useful models. Think social networks, protein interaction networks in biology, dependencies in large software projects, logistics, AI reasoning graphs.
Lots of complex systems.
Exactly. So if problems defined on these structures show critical transitions driven by constraint density, it's very plausible that the real-world systems they model might also exhibit similar behavior.
Like what? A network suddenly becoming unstable.
Precisely. Or a supply chain hitting a point where one more disruption causes a total breakdown. Or maybe even a large language model reaching a complexity threshold where its behavior changes abruptly. The Changbal Function framework, if it holds up more broadly, could potentially become a tool.
A tool for what? Predicting fragility.
Maybe. For identifying these critical thresholds in complex systems before they're crossed, understanding where the breaking points are, managing complexity, optimizing system design to stay away from those dangerous cliffs.
That framework, the Changbal function itself, seems pretty central to their contribution then. What specifically did they add regarding the function?
Well, the main thing was extending its application. It had been discussed mainly in the context of SAT. This paper explicitly applied the Changbal function model to K-uniform hypergraph 2 coloring. They formulated it specifically for this context.
How did that look?
They wrote it as SKX divided by 1 plus e to the power of x times xe bk. Here, x is the constraint density mm. And the key is that both the steepness parameter ek and the critical threshold bk are shown to depend on k, the uniformity.
Ah, so the shape and position of the cliff changed depending on the size of the hyperedges. And they found patterns in how AK and BK changed with K. I think that was figure 3.
Yes, exactly. And those trends were quite revealing. They found that BK, the critical density threshold, decreases as K increases.
Okay, wait, so for hyperedges connecting more vertices, a higher K, the cliff, the transition to unsolvable, happens at a lower density of constraints. It's harder faster.
That's what the data suggests, yes. It takes fewer of these larger, more complex constraints, hyperedges involving more vertices, to push the system over the edge compared to needing more numerous but smaller constraints.
Interesting. And what about AK, the steepness?
AK increases with K.
So higher uniformity, larger K, means a sharper, more abrupt transition.
Correct. The cliff gets steeper as the hyperedges get bigger. They even went so far as to suggest some approximate simple relationships based on their data, like maybe BK is roughly proportional to 1K and AK is roughly proportional to K, simple inverse and linear trends.
The fact that this same kind of S-curve behavior, these thresholds, appear in problems that look quite different structurally, like SAT and hypergraph coloring that feels significant, doesn't it? Suggests something deeper.
Absolutely. It's a major point they make. It led them to propose the concept of a generalized Changbal function. The implication is that maybe this function isn't just a convenient fit for specific problems, but perhaps it captures something fundamental about how structural complexity, broadly speaking, relates to the probability of finding a solution across a wider range of NP problems.
They also brought in some more, let's say, advanced mathematical ideas later in the paper, something about the function's derivative.
Ah, yes. Figure 4 shows that. They looked at the derivative of the Changbal function. Mathematically, the derivative tells you the rate of change.
Right.
And they showed that the derivative reaches its maximum value precisely at x equals bk, the critical threshold.
So the peak of the derivative confirms that bk is indeed the point where the solvability probability is changing the fastest.
Exactly. It's the mathematical confirmation that BK marks the center of the steepest part of the transition, aligning perfectly with what they called the empirical Changbal region.
And then there was that. Well, it felt almost like a leap into quantum physics, that analogy.
Yeah, that part is definitely more conceptual, maybe even a bit philosophical. They introduced this idea of viewing a problem instance, before you know if it's solvable or not, as being in a kind of superposed state.
Superposed. Like Schrödinger's cat.
Kind of like that, yes. They write it using quantum notation. Jaf A equals Ia he plus sa gen Pi. Here, P or represents the state the problem is solvable. Polynomial time verifiable solution exists, maybe findable, and NPO represents the state it has not yet converged to a solvable state PO.
Okay, so the problem exists in this fuzzy state, a mix of potentially solvable and not yet solved.
That's the framing, and the core idea is that when the problem's parameters, particularly its constraint density x, fall within that critical Changbal region, this superposed state collapses, similar to how observing a quantum system forces it into a definite state.
So the structure itself acts like an observation.
In this analogy, yes. The state collapses into P or solvable, with a probability given by the value of the Changbal function, fx, at that density. Or it collapses into the NPO state with probability 1 minus fx.
And crucially, collapsing into NPR doesn't necessarily mean impossible forever.
That's the really interesting twist they add. In their interpretation, the NPO state isn't game over. It just means it hasn't converged to P yet.
So it can change.
They propose that this NTO state isn't necessarily stable. It could potentially re-enter a superposition. This might happen just due to time passing, or maybe as more data comes in, or if the constraints shift slightly, or, and this is really provocative, through external interaction.
Like what? An AI trying different approaches.
Exactly. They suggest that things like AI intervention or even just accumulating more information could perturb the NPO state, potentially pushing it back into a superposition where it gets another chance to collapse, hopefully this time into the solvable PO state, perhaps with an increased probability.
So it becomes an iterative process, a dynamic system rather than a fixed yes-no.
That's the picture they paint. It reframes NP hardness not as a static wall, but maybe as part of a dynamic system that can eventually converge towards a solution, influenced by these structural thresholds and potentially by external nudges.
That really changes how you might think about tackling these supposedly intractable problems.
It really does. It introduces a motion of potential convergence over time or through interaction, which is quite different from the standard view.
Okay, let's try and wrap this up then. Bringing it all together, what's the absolute final takeaway from this deep dive into the Changbal function and these transitions?
I think the main point is that the study successfully demonstrates that this Changbal function framework, originally linked more to SAT, seems to apply really well to key uniform hypergraph 2 coloring too. They found clear empirical evidence for these sharp transitions happening within those narrow Changbal regions.
And the bigger message is that the structure of these problems, the constraints themselves, can impose a surprisingly predictable, almost deterministic pattern onto their solvability, even though we classify them as non-deterministic.
Precisely. The Changbal function is positioned not just as a neat curve fit, but potentially as a more fundamental mathematical bridge, a way to link the measurable structural complexity of a problem instance to the likelihood of actually finding a solution. And the hope is this bridge might span across many different types of NP problems.
And they laid out directions for future work as well.
Oh yeah, plenty. They talk about needing to derive theoretical bounds for these parameters, AC and BK, testing the function's validity on a wider range of NP-complete problems, applying it to real-world network data, and developing more formal mathematical tools, maybe using topology, to really understand how the solution space itself fragments or collapses near that critical threshold.
It's genuinely fascinating stuff. It suggests that even within problems that seem overwhelmingly complex and random, there's an underlying structural order that dictates behavior in these critical zones. That solvability isn't always a gradual difficulty increase, but can hit these sharp walls defined by the constraints.
Right, condensed into that surprisingly narrow window, the Changbal region. It makes you reconsider what complexity really means. Maybe it's less about infinite variation and more about hitting these specific, structurally determined tipping points.
And leaves us with that final thought. What does this imply for real-world complex systems? Could their stability, their failure points, also follow these kinds of sharp, structurally determined thresholds? And what about that quantum-inspired idea that problems we deem unsolvable might just be in a temporary state, waiting for conditions to shift, or maybe waiting for the right nudge, perhaps, from an AI to converge towards a solution after all?
It certainly flips the script on how we might approach intractability in the future. A lot to chew on there.
Absolutely. Well, thanks for guiding us through this complex landscape. It's been a real deep dive.